Now that we have a pixelated image correctly displayed as colored discs or disc-shaped LEDs, let's do the same thing for a video, a motion video, as opposed to a static image. And for that reason, I'm going to remove the displacement setup and replace it with a bump setup. I'll switch the displacement node to bump and plug the bump into the normal of my principled shader. And now I can preview in Eevee, and when I play the video, I'll get a responsive viewport. So let's choose a video file, or more to the point, an image sequence file. I'll turn on auto refresh and cyclic, set the frames to 197, which is the case for my particular animation, and I'll press play to cache some images. And we have the familiar image sequence. We have seen it before in previous videos, and just as in the previous videos, we have the issue of the image being scaled. The reason being, my available geometry is a square, whereas the resolution of this image is 1920 by 1080, making it a rectangle. So we're compressing the image horizontally. To fix that, in the previous video, I scaled the image to fit the geometry. And in this case, I'm going to do the opposite. To do that, I'll open the N panel in the 3D view, and here in Dimensions, if my square is 1 by 1, which represents 1920 by 1080, then I must adjust the X dimensions of my plane to fit. And to do that, I'll divide 1920 by 1080, giving me 1.7 recurring, and a correct view of the underlying video. However, we have scaled the geometry, but we have not scaled the UV map, which remains 0 to 1 horizontally and 0 to 1 vertically, which are now very different sizes. This is what brings about the difference in size of our pixels, which are now elongated horizontally. And to fix that, we need to manipulate the value fed to the width input socket of our UV grid node right here. And we'll do that with a math node. For now, we'll set it to divide by 1. So I see no change when I drop it onto the noodle. In fact, I don't. And now to correct the aspect ratio of the pixels, I should divide the tile size input by this width value. I'm going to copy and paste that into my divide node. And you'll see that my pixels have gone circular in this case, but the circle is being drawn inside a perfect square, just as I wanted. I can now play the video, and that looks pretty good. In fact, this issue of the aspect ratio is the reason for which, if you remember in a previous video, we saw that my plane was subdivided in a very particular way. Well, that's because I subdivided my plane when it was scaled to fit the video. If I remove the scaling and I go back to a square, you'll see this is the subdivision I had previously, and that is the reason for that odd subdivision. Moving on, the next step is going to be to create some square tiles instead of circular ones. Previously, we used the built-in gradient texture to create a circular gradient, or a spherical gradient as it's called in Blender, to create our round disc-shaped LEDs displaying the color of the underlying image. We're going to build the square tiles in a very different way, however. And let's begin with a separate XYZ node, and we'll connect it to the standard output of our UV grid node. And let's begin with some procedural work. I'm going to switch to a cycles render. I'm going to turn off the world lighting for a much faster viewport while using an emission preview. I'm going to increase the tile size so I can better see what I'm doing. Value of 0.2. Now the manipulations we're going to perform on the individual components of our standard vector will be carried out with math nodes as always. The first one will be a subtract node, and you'll see that when I manipulate the bottom value, I can essentially translate my gradient back and forth. I'm going to switch to an Eevee preview for a faster viewport, and I'm going to increase my tile size yet again to 0.5 just to better see what I'm doing. And there is the translation of our gradient. I'll reset the translation, And as we did before with a vector math node to control the scale of an image, in that case we used a multiply function. In this case we'll use a divide function. We'll turn clamp on, and I'll set the bottom value to 1 for now for no difference. But now as I reduce this bottom value, you'll see that I'm compressing the gradient to the size dictated by this value input into the second socket. I can show that to you by comparing it to the grid in Blender. Remove the scale of the plane, and now I'll mute this divide node. So now I'm back to working with a square plane and a square UV map, and things will be much easier to visualize. Here you can see the hard white cutoff of where we hit 1, which is then maintained across the rest of the gradient. And if I set that to 0.1, you'll see that coincides with 0.1 of a Blender unit from the left corner into here. If I want to set the edge line here, that would be 0.2, I assume. Let's try it, 0.2, and that looks good. I can then translate left to right, and the edge size remains unaffected. And we're going to use these functions to create the edge of our tile, and this to create some space around the tile, or grout or fugue, whatever you prefer to call it. For now, I'll set that to 0. We have the left side of our tile, and we're going to do the exact same thing to create the right side of the tile. All we have to do is to invert this X component gradient. And to invert a gradient, all you do is subtract that gradient from its maximum value, which in our case is our tile size. So we'll drop a subtract node onto the X noodle, swap the noodle into the bottom input socket of the subtract node, and connect our tile size into the top. And as simple as that, we have our inverted gradient, and the right side of our tile is ready to go. It will make sense to feed both the left and right sides of the tile the same values for space and for the edge sizes. So we'll drop in some value input nodes 1 and 2. I'll set the space to 0 for now and the edge to 0.1. Connect space into both of the subtract nodes and edge into both of the divide nodes. And now to combine the left and right edges, we'll use a math node. We'll set it to minimum and plug both the components into the available sockets, and there you go. We have the left and right edges of our tile. We can adjust the size essentially of the edges, and we can adjust the space between each tile horizontally. Let's tidy these nodes up a little bit because we're going to need to duplicate them and repeat these operations for the Y component. So I'll start by minimizing them all. Now I'll stack them up, as is my way. Drag them over to the right a little bit to get some more room. And let's tidy up the noodles with some reroutes. I'm going to tie together the 2 edge noodles, the 2 space noodles. I believe a space noodle is something else, isn't it? It's a toy, I think. And I'll tie together the 2 X component noodles like that. Now I can select all of my nodes, reroutes included, and Control-Shift and D to duplicate them and maintain the incoming connections. Now simply swap out the Y for the X, and there you have it. The top and the bottom of our tiles are ready to go, and they still follow the sizes set by our input nodes right here. And now to combine the left-right combination and the top-bottom combination, we're going to do the same as we did before. We're going to use a minimum node, plug all channels together, and we have a square tile with tapered edges, controllable space between the tiles, and we are looking good. As before, however, with the cones and domes, we have to pay some attention to the actual height produced by this height map, because we're getting values of 0 to 1, so this is going to be massively displaced. Luckily enough, the calculation to get the correct displacement for the height of these tiles is very simple, because it's the same size as the edge size. With a simple multiply node dropped onto this noodle, I'll plug in my edge size just like that, And now if we check a displaced preview, first I'll turn back on the world lighting. I'll turn off the preview, disconnect the bump node. I'm going to duplicate the bump node and place it down here and swap the duplicate for a displacement node. Set the mid-level to 0 and connect the displacement node to the material output. Turn on my subdivision. And now this result goes into the height of my displacement. And let's have a look. There we go. We've got some nice looking squared tiles with some tapered edges. The height looks good. For now, we still have our circular pixels because we use the mask from the gradient texture, and that's still controlling this mix RGB node. If I remove that input completely and set the mix down to 0, I get the background color, and 1, I get the image color. So I'll leave it set to 1 for now. I can reduce the tile size to see more pixels of my image. Still can't quite tell what it is. I'll make it a little bit smaller still. And you'll notice that what was previously a flat tile has turned into a pyramid. And that's because I adjusted the tile size, but I did not adjust the edge size. So now the shader is trying to give me edges of the same size as my tile, which doesn't make sense. So theoretically, this edge would actually finish here, creating a perfect triangle, but the right edge would be doing the same. And the minimum nodes here eliminate what would appear above, and it gives me a pyramid. So to get the flat tiles back, all I have to do is to reduce the edge size to less than half of the tile size. So anything less than 0.025 will do. If I key in 0.01, there you go. We still have the tapered edges, but now we have some flat surfaces correctly displaying our image. Let's take it a little bit further. We can soften the edges, or more to the point, round off the edges, as we did with our cones when we transformed them into domes. And we'll do it in exactly the same way. So I'll duplicate these nodes, drop them down here. I need to place these nodes between the final output of my tile group, which would be considered this group right here. This is my height regulation node. So I'll set that apart a little bit. Now I'm going to turn off the preview temporarily, bring these nodes down, and the output of this last minimum node goes into the top of the multiply node at the bottom of this stack, and the result of the square root goes into the top of my height regulating multiply node. Now a quick preview will show us we get our rounded edges. Very cool. Let's take the round edges one step further. We can also round off the corners to better suit the soft round edges. And we'll do that by combining the left-right combination and the top-bottom combination in a slightly different way. For now, we're using this minimum node. I'll keep that here. And we're going to create these round corners in something of a particular way. We're actually going to use the gradients created by these outputs as texture coordinates, which create a radial gradient. But as I said, we're not going to use the built-in gradient nodes. We're going to build the gradient by ourselves using a little bit of trigonometry. As always, math nodes, and quite a few of them. The first one we'll set to subtract. Let's plug in the, I'm going to call this the X component. This is the left-right combination of our tile. For now, I'm going to refer to this as the X component and this as the Y component. Let's plug our X component into the top of the subtract node. And now this value will represent the center point of our radial gradient. And I'm going to set this to 1. I'm going to turn off the preview. The next math node is a multiply node, and I'm going to plug the result of the subtract node into both the top and the bottom to multiply the result by itself, which is the same as raising to the power of 2. Now let's duplicate these two nodes and drag the duplicates down below because we're going to plug in the Y component into the top of the subtract node as before. We'll combine these two components with a math node set to add. Duplicate the math node, drop it to the right. plug in the result of the add node, and set this result to square root. The final math node is going to be a subtract node, and we're going to subtract the result of the square root node from 1. And now if I preview this result, you'll see that the corners are nicely rounded. So now let's plug that into our height map. Preview the principled shader again. And now I'm going to take the result of the minimum node from here and plug it straight into the output of this last subtract node. Turn on the preview. And if I zoom in, you can see that we are getting the rounded corners, but now we need another mask as we did before, because we want to remove the pixel color from the background here. So let's drop in math node, set to greater than with a threshold of 0. We'll plug the result of our homemade radial gradient into the top, and we'll use that result to drive our mix RGB node way up here by plugging it into the factor. And there we go. We can separate the color of the pixels from the background, and we have rounded corners, rounded edges, and we can still control all of these features. If you want to turn off your rounded edges, simply mute this bunch of nodes right here. Unmute to turn them back on. You can change the size of your edges, and the rounding of the corner will actually follow suit, to the extent that setting the edge size to half of the tile size will actually give us a perfect hemisphere again. Going to 1. We can introduce some space between each tile as we see fit. I'm going to go back to a bump-based Eevee preview for viewport speed. So my height input here goes into the height of my bump node. Connect the bump node to the principled shader and go back to an Eevee preview. You can see the video playing. And even as the video plays, we can come down here and play with these inputs to adjust what we're seeing. And here, for example, is a perfect use case for when we really need a fader node. You can see that the tiniest touch of this value input node changes the image entirely too much. I need more control. So let's add a fader node. Swap these noodles into the factor output. And now I can shift, click, and drag for much more control over my space input. And while I'm at it, I'm going to do the same for my edge input. Plugged into the factor, I'm going to delete the value input nodes. And now I have very fine control over both elements of the tiles. This video has run a little longer than expected, but before I wrap it up and call it a day, I want to add a new feature to the UV Grid node, which will allow us to offset horizontal tiles, and we can use that feature to create an effect much more similar to bricks, as opposed to bathroom tiles or floor tiles, which could be stacked one on top of the other in a square grid like this. The bricks in a wall, however, are arranged differently. Each alternate row is offset by half the value of the width of one brick, and we can do that within our UV Grid node. We'll make a little more space between the separate XYZ nodes and these main mathematical operations here. Now I'll need a duplicate of my group input node. I'll need one math node set to divide, and I need to divide the width by the height. I'm going to duplicate this math node twice, connect all the nodes in series, and set both of these duplicates to multiply. Now I'll plug the result of the snap of the Y component into the bottom of my second multiply node, and now I need to add the result of these calculations to the X component of my vector with a math node set to add. The result of the multiply node goes into the bottom, and there you have it. We have our offset by 0.5 because 0.5 is the value entered right here, meaning that we can control the offset by changing this value. So clearly we need to expose this value to the outside of the UV grid node to control it from the main node network. We'll do that in the usual way with a mix RGB node. We'll use its factor to create a clamped precision slider. I'll plug that into the bottom of my multiply node, and I'll rename FAC to offset. And now we can change the offset of the tiles, or in our case bricks, as we want to make them, from outside the UV grid node. But one final thing to address is the fact that, as you can see, the image is offset, as are the tiles. It can be interesting to offset the bump map and the tiles themselves while having the image stay where it is. Luckily, that is very easy to do. All we have to do is to remove that which we added here after the snap node. So I'll make a little more room. And if here I add the result of my multiplication, then here all I have to do is to subtract the same value. I'll plug the result of the multiply node into the bottom of the subtract. And now as I offset the tiles, the image stays where it is, and the color of the individual tiles actually changes as it updates the point from which it samples the texture underneath. Very, very cool. This feature may or may not be desirable at any given time, so we need an easy way to deactivate and activate it. As we did before with the step correct function, we'll simply multiply this value fed into the corrective subtract node over here by 0 to eliminate the correction, and then multiply by 1 to restore the value and restore the correction. So yet again, we'll expose a slider on the outside of our node, a clamped slider, connect the resulting factor socket to the bottom of our newest multiply node. Let me move these all in line. And this new factor socket gets called offset correct. This slider is precisely that, a slider, but very much like the step correct slider, it may be more desirable to use this as a switch as opposed to a gradual slider. So again, I'll drop in a greater than node with a threshold of 0.5 and drop it onto the offset correct noodle. My offset correct slider is now a switch where everything below 0.5 is off and everything above 0.5 is on. And that'll do it for this video. Next, we'll continue with the idea of the procedural bricks. We'll look into two different ways of creating procedural brick materials using a pre-made bricks texture set, a PBR texture set, and a fully procedural way, even though that could possibly be for the following video. For now, thank you all very much for watching. If you liked the video, please leave a like. If you found it useful, please consider subscribing to the channel for more video content like this, and I'll look forward to seeing you in the next one. Take it easy.